Welcome friends. So today's topic is on water. Okay. So before starting our today's topic, I would like to take answer of last lecture. So I have asked you two questions where meter of H2O unit is used, and the second question was if you pour mercury in a glass, the glass does not become wet. Why so? Okay, so I have not received any comment. Maybe two reasons are there that nobody have watched full video because it is 53 minutes long video. Don't worry, this will not be that much long. And secondly, nobody knew. Okay, so whatever it is, the meter of H2O where we are using wherever we are wherever we want to measure the height of water, suppose in the tank, okay, how much water is there, or say if you see the oil tankers or milk containers, oil containers, water containers, so you cannot go deep into the vessel. Big containers are there, so you cannot go deep into the vessel. So what is there? The big scale is there. That scale gives the unit, means that scale measures and the unit is meter of H2O. That is the answer of first question. And second answer, that glass does not becomes wet when you pour mercury into that. That is because of the cohesive bond. Okay, there are in chemistry there are two types of bonds. One is cohesive bond, one is adhesive bond. So water is in water adhesive bond is stronger, whereas in mercury cohesive bonds are stronger. So because of that, it cannot match with the other surface. Means it will make a membrane type. Like if you see the surface tension theory in deep, you will understand. But the answer is it is due to the cohesive bond in presence in the mercury. Okay, so these are the two answers. If you want to have good details particularly in these two answers, you can write in the comment box. I will tell you in detail also. Okay, so let's start today's topic, and today's topic is on water. Okay, so 70% of the space, means 70% of earth is occupied by water. Okay, 61%, our body contains 61% of water. Okay, so it's very important element. When I have heard about God's particle few years back, okay, when experiment was done in hydrogen collider. So at the time when I heard first time, I thought what is there, means what is God particle, anything. And anyway, water is also God particle. Then I thought, how, means of course it is a God particle because it does not have shape, or say the element water does not have specific shape, no color, tasteless, okay, and you cannot live without it. So many good qualities are there, but we are not here to discuss about other aspects. We are here to discuss about thermodynamic aspects of water. Okay, so we will start today's topic. So today's topic is TS diagram of water. Okay, so first of all, TS diagram. Why we study TS diagram of water? Because it describes the thermodynamic property of water. What are the thermodynamics property? Property like pressure, temperature, specific enthalpy, entropy, okay, boiling point, freezing point. All these are thermodynamic properties of any material or any element. Okay, so TS diagram is useful to understand the thermodynamic properties of water. Okay, so we will see that because it is very useful. Okay, so where it is useful, say if you are working in a steam power plant, okay, say steam power plant works on Rankine cycle, so you should know the TS diagram of water, or you can say that it is a TS diagram of steam also. Okay, so TS diagram of water or TS diagram of steam. So there it is used. So we will see what it is. Now first of all I will ask, say, what is boiling point of water? Okay, so if you are thinking that boiling point of water is 100 degrees Celsius, that is partially correct answer. Why it is partially correct? Because it is every time it should not, or it is not necessary that boiling point is 100 degrees Celsius. If you go on a hill, their boiling point is different. Okay, if you go underground, their boiling point of water is different. So boiling point of water depends on the pressure also. With respect to pressure, boiling point is defined. Okay, so 100 degrees Celsius, suppose atmospheric pressure is 1 atmosphere or say 1 bar. So at 1 atmosphere or 1 bar, the boiling point of water is 100 degrees Celsius. Okay, so if you go say 1.5 bar, okay, say if you go at 1 bar, say here bar, say here boiling point. So say at 1 bar boiling point is 100 degrees Celsius. Okay, so if you increase the pressure at 2 bar, say boiling point will be 140 degrees Celsius. If you increase to 3 bar, it can be 180 degrees Celsius. Okay, so as pressure increases, temperature also increase according to the P is proportional to T. Okay, so if you increase the pressure, boiling point means temperature also increase, boiling point also increase. So 100 degrees Celsius is at 1 bar pressure. Okay, so it is not whenever anybody is asked you what is the boiling point of water, you should ask reverse question that at what pressure, or directly you can answer that at 1 bar pressure it is 100 degrees Celsius. At other pressures it can be anything. Okay, so that is about the boiling point. Then next I want to tell you about pressure. Okay, but here we are not going to discuss about pressure in detail, but you know, or say pressure in thermodynamics we are defining pressure in 3 ways. Okay, say absolute pressure, gauge pressure and atmospheric pressure. So absolute pressure means absolute zero pressure. Okay, absolute zero pressure is termed as absolute pressure. Now what is atmospheric pressure? The pressure with reference to absolute pressure means absolute zero pressure, that is atmospheric pressure. What it is 1 atmosphere or say 1 bar. So that is atmospheric pressure. And what is gauge pressure? Gauge pressure is nothing but pressure above atmosphere or below atmosphere. Okay, so generally if pressure is above atmosphere, we are telling it as, or we called it as gauge pressure, and if that pressure is below atmosphere, we called it as vacuum pressure. Okay, so 3 are there: absolute pressure, atmospheric pressure, and gauge pressure. Say if I want to draw, say this is absolute pressure, say absolute zero pressure, then say this is atmospheric pressure. This is atmospheric pressure line. Okay, this is absolute zero pressure. So the atmospheric pressure is with reference to absolute zero pressure. This is termed as gauge pressure. This is gauge pressure. So this gauge pressure, say pressure at point E is nothing but pressure at point A is nothing but atmospheric pressure plus this gauge pressure. Okay, say this pressure B, this is termed as vacuum pressure. So pressure at point B is nothing but atmospheric pressure minus this vacuum pressure, that is pressure at point B. Okay, so this is just some fundamental about pressure. because you should know. Okay, so that's why I have told. So this is the thing. I'll rub it. Now after pressure, we will see, say, TS diagram of water. What we are discussing here, TS diagram of water. In that, T represents temperature, S represents the entropy. So TS diagram of water. So on the x-axis we are having entropy S, on the y-axis we are having property T, that is temperature. So TS diagram of water. Now in that TS diagram, say what is entropy? Say temperature, you know, okay, it is a measure of heat capacity. Okay, so that is temperature. Entropy is in layman definition, it is just a randomness of molecules in any matter. Okay, so generally in study or in thermodynamics we define entropy not as a property, but means that is a property, but we are not defining as a single entropy S. Always we define in terms of delta S, means change in entropy. Okay, so say there is an equation ds or say dq by dt is equals to dq by dt is equals to delta S. So change in entropy is equals to del q, means change in the energy, okay, divided by change in the temperature. Okay, so whether you are adding heat or removing heat, so that is delta q, and the temperature is increasing or decreasing, that is delta T. Okay, so this defines the delta as the change in the entropy. Okay, so if you adding heat, if you are adding heat means Q is increasing, that means delta S is increasing. If you are removing heat, so removing heat means temperature also will go down, delta Q also will go down, so delta S will be less. Okay, so depending upon the entropy increase, depending upon the heat addition and heat rejection, entropy will change. Okay, so that is regarding dq by dt is equals to delta S. There is another, see, heating is nothing, always it cannot increase the temperature. Suppose there is a specific definition of sensible heating. So what is sensible heating? Sensible heating means when you heat, when you give heat to any substance, its temperature is increasing. Okay, that is sensible heating. But odds are there. Suppose, okay, that is the question, you search for that. Okay, which is that element or which is that process, okay, when giving the temperature, when giving the heat, the temperature is not increasing. Suppose if you give heat to water, so its temperature is increasing 30 to 32, 35, 36, 40, like that. If you give heat to air, its temperature also gets increased. So which is that process, or when if you give the heat, temperature will not increase? Okay, so which is that occasion, situation or process? Okay, so think about that. Okay, so that is regarding the sensible heating. Now we will see the TS diagram. Okay, so at 0 degree temperature, entropy is taken as 0. Okay, so now when, see here, this is the curve. Now here, see, temperature entropy diagram means, say TS, yeah, say TS. Now in TS diagram, if I draw a line like this, that what does it mean? It means it is a constant temperature process. Constant temperature means isothermal process. If I draw a line like this, it is a constant entropy process. Constant entropy means isentropic process or reversible adiabatic process. So say 1 and 2. So S1 is equals to S2 here. Here T1 is equals to T2. Okay, so if here, say here horizontal line is there. So what does it define? Here temperature remains constant. Here and here temperature is constant. Here and here temperature is not constant. Okay, so this is regarding horizontal and vertical line in specific diagram. So now here, see here, which is this line? This is a pressure line and pressure is constant. Okay, so say pressure I am taking, this is say P is equals to 1 atmosphere. P is equals to 1 atmosphere. Okay, so this is a pressure line. Now at 1 atmosphere, if you give heat to a water, there is a specific amount of water is there, say 1 liter or 10 liter. Okay, now at 1 atmosphere pressure, if you give heat to water, what happened to its temperature and entropy? So if you hit, see this, how this diagram came. First, we don't have diagram by default. Okay, we have to draw all the diagrams or all the charts or tables. Okay, have you thought about that? From where all these tables, say steam table, refrigeration table, or charts or graphs came? All the charts and tables came by having, means after completing the experiments. Okay, first of all, first we don't have, at the starting we don't have all the data. Suppose who told that at 1 bar boiling point of water is 100 degrees Celsius? It's not fixed. We have seen that, we have observed, we have done the experiment. Then in every condition, then we have realized that at 1 atmosphere pressure, temperature means boiling point of water is 100 degrees Celsius. So all the data in the any table or all the charts are made by experiments. Okay, so experiments have done before, based on that these tables and charts are made. So first of all, suppose there is nothing, say here temperature, entropy and pressure 1 bar I am keeping constant. Now if I give heat, its temperature and entropy will behave like this. Okay, so temperature is increasing, entropy is also increasing. At a specific point, this point, any point, at a specific point, okay, so at this specific point, now temperature is not increasing. So, but entropy is increasing. We are continuously giving heat. So after this point, temperature is not increasing, but entropy is increasing. And after some another point, again temperature and entropy is increasing. Okay. So by experiment we can see that this at 1 bar pressure, this point is 100 degrees Celsius, which is boiling point of water. So from here water start boiling. Okay, at this point water starts boiling, and this is, so the portion before this point, this portion is known as liquid region, or say subcooled liquid region. Okay, subcooled liquid region or liquid region. Then in this there is liquid plus vapor both, because from here water starts boiling, so water is also there and boiling means steam is also there. So here water starts boiling, continuously we are giving heat, and at this point, again at this point, all the water converted into the vapor, and from here its temperature again increasing. So this line we got by experiment, by giving heat. Experiment, simple experiment, we have a specific amount of water, we are giving heat to water, so, and we are having say thermocouples or temperature sensors, so we can get these data. Okay, so at 1 bar pressure or 1 atmosphere pressure, this is the line. Now I am increasing the pressure at 2 bar pressure. At 2 bar pressure I am doing same experiment again. So it is coming like this. At 3 bar pressure or 5 bar pressure, say 3 bar, 5 bar, I am getting these type of lines. Okay, Now if I connect these points, boiling points at different pressures, what I will get? I will get curve like this. I have to buy new marker. So I will get curve like this. Okay, so that is this curve. Okay, so I have written here, this is a liquid region, this is a vapor region. Why? Because on this side of this curve there is a liquid, on this side of the curve there is a vapor. Okay, I have written VAPOR, you can write VAPOR or POUR, both are correct. Okay, now this line, there is one point, so before that point, this is point, this is known as critical point. Okay, I will tell you afterwards. So this line, okay, this line, left line is called saturated liquid line. Okay, saturated liquid line means 100% water is there. Okay, saturated liquid line. And this right side line is called saturated vapor line, means 100% vapor is there. Okay, so this side 100, this before means behind this line, and on this line 100% water is there. This side of the line 100% vapor is there. In between this region, this dome, in this region there is liquid plus vapor, both phase are there, liquid plus vapor. So this is known as sensible heating, because you are giving heat, temperature is getting increasing. This is phase change process. Why? Phase change means phase is changing. Here phase is water, here phase is vapor. So phase change process happens. Remember, whenever phase change process occurs at constant pressure and constant temperature. Okay, so you can see here temperature at point 1. Say if I describe this at point 1 and point 2, if I see P1 here, this is a pressure line, so pressure is constant throughout this line. If I see here T1 is this one, say 100 degrees Celsius, T2 is also 100 degrees Celsius. So process 1 to 2 is a phase change process. Okay, it converted from liquid to vapor. So here I have written X is equals to 0. What is X? X is defined as dryness fraction. Okay, so it defined by how much amount of water is there and how much amount of steam is there, means how much water vapor is present in the mixture. Okay, so here dryness fraction is 0. Okay, 0% dry, fully wet. 0% dry means, so 0% dry means what? Okay, here X is equals to 0, dryness fraction is 0. So here dryness fraction is 0, here dryness fraction is 1. So here dryness fraction is 0 because it is saturated liquid, fully liquid is there, no dryness is there. That's why here it is 0, and here this line is called a saturated vapor line. So it is completely dry, no water vapor presence are there, no moisture. That's why X is equals to completely dry, that is X is equals to 1. Okay, so this is X is equals to 0, means dryness fraction, nothing dry is there. Okay, saturated liquid is there, and here saturated vapor is there. So what is dryness fraction? Here dryness fraction is 0, here dryness fraction is 1. So why here dryness fraction is 0? Because this is saturated liquid line. So saturated liquid line means fully liquid, full water, no vapor is there. Okay, because it's about to boil. Okay, here it starts boiling, so fully water is there, so X is equals to 0. Now when it starts boiling, okay, phase is changing from liquid to vapor. So vapor means dry, water means wet, vapor means dry, or air is dry, water is wet. So it starts going from here to here. So 0, 0.1, 2, 3, 4, 5, 0.9 and finally 1. So on the saturated vapor line, dryness fraction is 1. That means no water vapor present at these points. Okay, that is dryness fraction. That is all about dryness fraction. Now after the dryness fraction, here enthalpy of vaporization is there. Okay, now what is enthalpy of vaporization? HFG I have written, that is enthalpy of vaporization. We will see in detail when we will discuss say steam table. Okay, I will make another video how to read steam table. In that we will see what is HFG, HF, HG, everything. But what is that? That is enthalpy of vaporization is nothing but amount of heat required to convert a specific amount of a liquid into water. So at 1 atmosphere, 2257 kilojoule per kg amount of heat if you give to water, it will convert into the vapor. So for water at 1 bar, enthalpy of vaporization is 2257 kilojoule per kg. 1 kg means 1 liter water is there, you are giving 2257 kilojoule of heat, it will convert into the vapor. Okay, so that is an enthalpy of vaporization. Now I have told you in the rough diagram, see this is the enthalpy of vaporization, okay, at say 1 bar pressure. If you increase the pressure, say 2 bar, enthalpy of vaporization, this enthalpy of vaporization is less. Okay, if you again increase the pressure, enthalpy of vaporization is more or less. So if you go forward continuously, as you increase the pressure, the enthalpy of vaporization, that means the amount of heat required to convert water into the liquid, is less. Understood? That amount of heat is required, amount of heat to convert water into the vapor is less. So here this much amount of heat is required. Here 2257, here only this much amount. At this point at this point, say if you reach the pressure this one, that is you can directly, means at that pressure water directly becomes vapor. Directly, no need to give any amount of heat. What is that pressure? That pressure is 225 bar. Okay, 225 bar, 225 bar. So that is also known as critical point. Here I have written, that is known as critical point. So at critical point, no amount of heat we have to give, means enthalpy of vaporization is 0. The water is directly converted into the vapor at that pressure. Okay, so that is about critical point. There is one line also will be there. Say there is a specific triple point line. Say here, say this line is triple point line, that we will see in steam table video. But what is the triple point and critical point? You should have the proper idea. Triple point of water means what? At the temperature and pressure at which all three phases are there, means there is ice also, water also and vapor also, steam also. Okay, so where all the three phases, solid, liquid, gas, are present, that point is known as triple point. And critical point is when liquid is directly converted into the vapor at a specific pressure. That is triple point of water. For water it is 225 bar. Okay, so that is about triple point and critical point. So I think you have understood about TS diagram of water. Okay, TS diagram of water, critical point, saturated liquid line, X is equals to 0, enthalpy of vaporization is always decreasing. Here liquid is there, here vapor is there, here liquid plus vapor is there. Okay, I told you about boiling point also, it's not always 100 degrees Celsius. If you increase the pressure, boiling point also increase. If you decrease the pressure, boiling point also decrease. Okay, So all those things I have told you, these things will be useful when you study Rankine cycle or steam power plant. There is a specific subjects also there, okay, in mechanical and thermal engineering. Power plant engineering subject, specific subject is there. So in that you will learn all these things, okay, enthalpy of vaporization, specific heats and everything. So that's it for today's class. I hope you have understood. Okay, if you have any doubt, please write it in the comment box, or you can mail me at Chirag, CHIRAGVMISTRY @gmail.com. Okay, so mail your doubts, or you can give suggestions and feedbacks also, most welcome. And you can write in the comment box also if any doubt is there, okay, regarding the TS diagram, how it made, okay, why it is dome is like this for water. So I have told you like this it came, and if you increase the temperature also increase, say here 100, say here 120, here 140, 180, like that it will increase. That value is not, I am just writing, but it will increase with the increase of pressure. Temperature also will be increased. So that's it for today's class. I hope you have understood. If you have any doubts, you can comment or email me. Okay, so before going again, I wanted to ask you some questions I have written. Yeah, so if you add salt in the water, so question is like, okay, say if you add salt in the water, its boiling process will be faster. That is true or false? If you are saying true, why it is so? If you are saying false, then also you have to justify. Okay, so adding salt increase the boiling process of the water. True or false, and justify your answer. And if you add salt in the water, what is the effect on the water content volume? Okay, suppose one glass of water is there. If you are putting 2 spoons of salt into that, what is the effect on the volume of water content? Okay, and that's it. And what else? Yeah, say if water is freezed, what will happen? Compression will happen, expand will happen, it becomes heavier, or okay, 3 options compression, expansion, and it becomes heavier. Okay, and sensible heating, I have told you during the lecture that which is that process or occasion or situations when you are adding heat but temperature is not increasing. I told you, whenever you are adding heat, suppose water, if you are adding heat, temperature will increase 30, 40, 50, like that. But which is that process in which if you are adding heat, temperature is not going to increase. Okay, so these 3 questions I have told you. So that's it. Hope so you have understood and it will be useful. If not, sorry, I have tried. Okay, if you have not understood, then also okay, but water is very important component and element of our life, so have a knowledge of it. If not thermodynamic or engineering knowledge, have a knowledge of water, how it affects our life. Okay, because see, it helps. You cannot live, you can live without food, you cannot live without water. So if you want to explore more on water, you should explore more on water. How much water you have to drink in a day. Okay, suppose if you don't eat food, you can survive, but if you don't drink water, I think it's 3 days. Yeah, I have read. So in 3 days, for 3 days, if you don't drink water, you will die. Okay, so have a proper knowledge of water. Say it helps in our digestion system, it helps to make blood, it cleans our blood. Okay, everything. Okay, so have a knowledge of water, both thermodynamic engineering knowledge also and other science knowledge also. It is very useful. Okay, thank you.